Hi, I'm Feng from College of Control Science and Engineering in Zhejiang University. The project I'm going to talk about today is motivated by a real-world application that optimizes the operation of a large-scale chemical plant. We are working on this problem since we realize that it is subject to strong inherent uncertainty, which is very difficult to estimate its underlying probability distribution. So we decided to use the distributionally robust optimization approach to solve this problem. Recently, predictive maintenance receives extensive attention from the process industry. This means that the process data is used to build data-driven equipment health models, which can tell us how the equipment degrades over time and when it will fail. Only having this predictive model isn't enough. We need to use them to inform decision making. So we have prescriptive rather than predictive maintenance. Then we focus on the integrated production and maintenance scheduling problem. Production and maintenance are two different activities which are typically addressed separately or sequentially. However, due to their close interactions, it's obvious that there are many benefits if we can optimize them simultaneously. As mentioned before, our work is motivated by a real-world application. Specifically, we focus on optimizing the operation and maintenance of the cracking furnace system, which is the core of ethylene plant. Cracking furnaces convert diverse hydrocarbon feedstocks to smaller hydrocarbon molecules. However, during the cracking process, the coke is generated as a byproduct which accumulates on the inner surface of furnace tubes over time, and consequently reduce the efficiency of process. So occasionally, we need to clean the furnace to make sure that the coke thickness does not exceed the given limit. Lastly, in this work, we focus on optimizing the operation and maintenance of cracking furnaces. To track and predict the equipment health state, we apply such a continuous state model of remaining useful life (RUL) that is a common measure of equipment health. This is a popular class of RUL models which is based on stochastic processes such as the commonly used Wiener and Gamma processes. RT here denotes the RUL as time t. Mu is the degradation rate. Delta t is the time interval between time t and t minus 1. Wt indicates the uncertainty in degradation process. The degradation rate mu can be computed by an affine function over x, which always represents the production amount. So when such a model is built, we typically assume that the distribution of the random variable W is given or can be estimated from the history data. But this is not the case here. When we look at the data, what I show here is the histograms of two furnaces whose data were collected over 3 months. In each plot, the blue histogram shows the data in the first half of the 3 months, while the orange one shows the data in the second half. We expect them to be similar, but they are not. Especially the second one is very different. This means that the probability distribution of random variable W changes over time, which makes it very difficult to estimate, and this motivates us to apply distributionally robust optimization approach in this problem. Here I just summarize the ingredients to build a scheduling model and highlight some model features. Our model is based on a deterministic model proposed by Biondi et al. And extend it to consider multiple maintenance options and the health stage dependent production capacity. The critical part of this model is the stochastic equipment health model. Y is the binary variable, denoting whether the equipment is operated or not. X is the production amount. F denotes the restoration of RUL from maintenance, and W is still the uncertain parameter. Although we haven't exactly know the probability distribution of W yet, we do know its support, so we can formulate an uncertainty such as such a simple box. Also note that the degradation only occurs when the plant is operating. which means that W is the endogenous uncertainty. Fortunately, we can reformulate the problem with auxiliary variables, in this case to retain the fixed uncertainty set. Then we express the DRO problem in this compact form. X is a vector of continuous variable, and Y is a vector of binary variable. And T represents the decision stage here. We have the uncertainty parameter Ct, which represents the uncertainty parameters up to stage T, which is contained by the polyhedral uncertainty stage Ct. The constraints are formulated in a robust optimization manner, which forces a solution to be feasible under every possible realization of Kc within the uncertainty set. But the objective function is formulated in a DRO manner. This means that we do not know what the true distribution Pkc is, but we can formulate the ambiguity set, which is skewed P, and we assume that the true distribution Pkc is contained by this ambiguity set. So we minimize the worst expected cost with respect to this ambiguity set, and this is what this max does. Here we choose the Wasserstein ambiguity set. dW denotes the Wasserstein distance, which measures the difference between two distributions. P eta is the empirical distribution, and the epsilon is the radius of Wasserstein ball, which is the parameter that the decision maker can adjust to change the size of the ambiguity set. So this ambiguity set contains all the distribution whose Wasserstein distance to the empirical distribution is less than or equal to epsilon. With this definition, it's quite obvious that DRO is a generalization of robust optimization and stochastic programming. When epsilon equals 0, what you obtain is a sample average approximation, which is commonly used in stochastic programming. When epsilon is sufficiently large, the robust optimization is recovered. To solve this problem, we first apply the decision rule approach to model the mixed integer recourse. So we use the concept of lifted uncertainty to construct the discontinuous piecewise linear decision rules for continuous recourse and piecewise constant rules for binary recourse. Then we use the scenarios to define the empirical distribution, and which allows us to reformulate the objective function in the following form. I won't go into details here, but what I want to emphasize is that we derive the formulation that depends on the scenarios. So its size goes with the number of scenarios, but it only applies to the objective function rather than the constraints, since the constraints are formulated in robust optimization manner. Then we can further use the duality-based formulation, and the model is eventually reformulated into a mixed integer linear program that can be solved using off-the-shelf solvers. Now we first apply the proposed methodology to an illustrative example. This is just a small state task network involving two different reactors, which can perform different reactions and also have different maintenance options. We have 120-hour schedule horizon with each time period being 12 hours. That means that there are 10 periods in total. First, I'd like to show the importance of the multi-stage recourse, which is the main feature of this model. Here we compare three different cases of recourse. In the first case, we don't consider any recourse, while the second instance only considers the continuous recourse, and the third one considers both the continuous and the binary recourse. So as expected, you can see the optimal value improves by introducing more recourse. And the difference is quite large from the static case to the last case. The relative improvement is around 12%. However, the computation time also increases significantly. And the number you see in this table are obtained by using some approximation strategies to reduce the decision rule complexity, including that we only consider uncertain parameters from the previous delta t stages and restrict the information base of the recourse based on the initial RUL values. You can see that the integration of strategy 1 and strategy 2, which the last instance uses, can lead to the most cost efficiency performance. In fact, the instances in this table are also solved using this kind of strategy. Then we solve a series of DRO instances with different values of action, and this figure shows the corresponding optimal values. As expected, the optimal value of DRO increases monotonically as action grows. Since the worst distribution within the ambiguity set becomes even worse. In particular, the optimal value of DRO is the same as SAA and RO when epsilon equals 0 and is larger than 150 in this case, respectively. We also apply our methodology to the industrial case study. We consider the furnace system composed of 3 furnaces which can process 3 different raw materials. We have 28-day scheduling horizon, and we also have 1 year of available history data. So there are 12 scenarios in total. This table shows the computational results of different models, and similar to the previous example, you can see that the optimal value increases with a larger epsilon. Then we compare their actual sample performance, which is our main concern. Since we do not know the true underlying distribution, what we do here is using kernel density estimation to estimate the distribution, and then consider it to be the true one. We randomly sample 100 scenarios from the distribution and use these scenarios to evaluate the actual sample performance. We choose 4 different bandwidths of the Gaussian kernel to obtain different distributions. The resulted actual sample performance are plotted on the right. You can see that the average cost curve doesn't increase monotonically. Instead, we can see that there is minimum when epsilon equals 1 in all the 4 cases. This means that DRO with epsilon equals 1 can achieve the best actual sample performance in this case. To give more intuitions how the solutions of SAA, RO, and DRO differs, we show their Gantt charts. In each chart, we show how the corresponding schedule adjusts according to a real relation of uncertainty. Note that these red blocks denote the decoking operation. Obviously, the main difference between SAA and the RO solutions is that in SAA case, we perform the decoking operation in period 12 only when it's necessary, while the RO solution is much more conservative, which always performs the decoking operation in period 11, no matter how the furnace degrades. In contrast, the RO solution actually provides a compromise between SAA and the RO solutions, which turns out to be a better option. You can see that the decoking operation is performed in period 11, only when it's necessary. So it's more conservative than SAA, but is less conservative than RO solution. Finally, we'll achieve some conclusions. In this work, we consider the integrated production and maintenance scheduling problem with stochastic equipment health models. To account for the degradation uncertainty with unknown probability distribution, we develop a multi-stage DRO model with one-16 ambiguity set and apply a decision rule-based approach to obtain a tractable approximation. We also demonstrate the effectiveness of the proposed approach in an industrial case study, and the results show that DRO can lead to better actual sample performance. Thanks for listening. I will be happy to take any questions. You can email us at either of these 2 addresses. Thank you so much.